Hello and welcome you all for today's class. It is about the solid state of class 12th. In this chapter, we are going to know about the characteristics of solids, what are the solids properties, how they are different from the other states, liquids and gases, and can be able to classify the solids. If there are crystalline solids, what are the types of crystalline solids? How the lattice, crystal lattice is arranged and the crystal points can be found out in the solid, and what is meant by unit cell, brevis lattices and lattice points of a unit cell and so on. So here the characteristics of solids. Solids are rigids. Solids have definite shape and volume, whereas liquids, particles are haphazard and there is less attractive forces between the particles. These are the points that you have known already. So solids can be defined as they are those which are having definite shape, volume, rigidity, incompressibility and high density. Now solids are having constituent particles very closely packed and therefore they occupy the fixed position, and the distance or the gap between the particles is less, that means they are closely packed. So the voids or the free spaces between the particle is less. That is the reason why they are having definite shape and definite volume. You can look into the shape of or arrangement of particles in solid. So this is the way the particles are arranged, one over the other, without leaving much space. Always particles are considered to be the spherical ones. It all goes with the different models of atoms, and we consider each one is like a sphere. Now, what are the different kinds of solids that we can have? Some solids deviate from the important property like arrangement. So in case of solids, we can classify them into crystalline solids and amorphous solids. Crystalline solids, you can see the quartz is a crystalline solid. The one which you can see here, quartz, is a crystalline solid. And some are amorphous solid. They are like glass. Both are called solids, but they differ in their arrangement. What way they are different? Let us see the arrangement of them, right? The arrangement, constituent particles are orderly arranged in case of crystalline solid. Crystalline solids, each particles are orderly arranged, as you can see here. They have long range order is the better way of saying it. So they have sharp melting points. Any solid you take and determine the melting point of it, you get a sharp melting point, right? So they are anisotropic in nature. Anisotropic means what? Some of the physical properties which are measured from different directions are different. They get different values. This is called anisotropic. Crystalline solids are anisotropic. That means if you measure some property like refractive index, it is different at different angles, or conductivity value, it is different at different angles of a solid. But amorphous solids are not so. Now coming to the other properties of crystalline solids. So these are considered as true solids. Amorphous solids are called pseudo solids, but here they are called true solids. These undergo a clean cleavage. When you cut a solid, so they have got a sharp edge. So this is meant by clean cleavage. Crystalline solids have definite heat of fusion. So the diamond, graphite, metal like iron, cobalt, copper, etc. Ionic compounds like NaCl, ZnS and KCl, etc. they are having a definite heat of fusion. What is heat of fusion? When you take 1 kg of a solid, if 1 kg of solid, the heat required for conversion of 1 kg of solid into its liquid at its melting point, that measure is called heat of fusion. They have definite heat of fusion. That means they are having fixed heat of fusion. But in amorphous solids it is not so. That's how they differ. So you can see the crystalline solids here, they have got clean cleavage and have definite heat of fusion. So here some examples of diamond and graphite is being taken. They are the elements and some compounds are also there, KCl, ZnS. All these are pure, they are pure substances, pure solids, they are having sharp melting point. Now coming to amorphous solids. The constituent particles have no regular arrangement and they have short range order. They have short range order. That means they are not regularly arranged. The particles are not regularly arranged. They are regularly regular. You can see that the same particles are not arranged in the same way throughout. So another thing is they have no sharp melting point and they are isotropic in nature. Anisotropy, isotropy. Crystalline solids are anisotropic and amorphous solids are isotropic in nature. So they are considered as pseudo-solids. Pseudo-solid means not true solids. They are called supercooled liquids. They are called supercooled liquids. Right? So glass is an example for amorphous solid. Glass, it is an example for amorphous solid. It is not having sharp melting point. So amorphous solids have heating become crystalline at some temperature. They may attain crystallinity. Some of the compound, some of the material can undergo is this kind of change. The amorphous solid on heating become crystalline at some temperature. Glass objects of ancient civilization appear milky. This is what we find, and this is the reason for it. Glass is an amorphous one, but in the long course of time, the amorphous glass attains crystallinity. Because of this, it becomes milky. Old or ancient civilization glass objects are appearing milky because of this reason. Amorphous solids have fluidity. Amorphous solids have fluidity. So this is also we can able to observe the glass windows in the old building appear thick at the bottom. So the window panes which are vertically kept and arranged, they seems to be thicker at the bottom. They are thicker at the bottom. So this is what our observation is. So therefore, they are not called true solids. They are amorphous solids or pseudo solids. Now, coming to the type of crystalline solids. Crystalline solids can be classified into 4 types depending upon the interparticle force of attraction. One is molecular solid. In molecular solid, constituent particles are polar or non-polar molecules or hydrogen bonded molecules. For example, water in the form of ice is a molecular solid. So between 2 water molecules there is hydrogen bonding. Right? If sulfur, for example, sulfur is solid because it is a said bulky molecule, it is having van der Waals force of attraction. So usually molecular solids are having low melting point. Forces of attraction is dispersion force or dipole-dipole attraction or hydrogen bonding in case of molecular solids. They are having low melting point and boiling point. Usually they are insulators, right? So this is how the constituent particles which are present in iodine. Iodine is a solid, I2. Because of the bulkier iodine atom, they attract each other because of van der Waals force of attraction, right? Now, the another type of crystalline solid is ionic solid. Ionic solid constituent particles are ions. In NaCl, sodium ion and chloride ion are present and they attract each other. There is electrostatic force of attraction. Since each ion is held to many of the ions surrounding, the bonding is strong and therefore they have high melting point and boiling point. They are electrical insulators in the solid, but they are conductors in aqueous solution or molten state. It is because of rigidity of ions. So once they are in the solid state, they cannot move. Therefore, they are not conducting. But in the molten state or in the aqueous state, they can show this mobility and therefore they are electrical. They are conducting electrical current. So you can see the constituent particles, how they are arranged in sodium chloride. Now, based on again another type of solid is metallic solid. So in metallic solid, constituent particles are positively charged metal ions and the free electrons, or kernels and pool of electrons. This is what the arrangement in case of metallic solids. Metallic solids are held by metallic bond and they have high electrical and thermal conductivity. The free electrons are responsible for electrical conductivity, and vibration of kernels also is responsible for conduction, thermal conduction. They are malleable and ductile. They slip over each other, therefore they are malleable and ductile. They have high melting point and boiling point. For example, iron, copper, silver, magnesium, etc. All these are having high melting point and boiling point, right? So the metallic solids are the another type of solids. Now the fourth type of crystalline solid is covalent or network solid. Covalent network solid consisting of the covalent bonds throughout the arrangement. So constituent particles are neutral atoms, but the force of attraction is covalent bond. Diamond is an example for this. It consisting of neutral carbon, but carbon forms 4 bonds with another carbon atom, and the array of this covalent bond is present in the diamond. But they are having high melting point because of this strong covalent bond, and they are insulators, diamond, quartz, and silicon carbide, SiC, aluminium nitride, AlN, all these are insulators. But exception is graphite. In graphite, each carbon is held to only 3 carbon atom, letting 1 electron free, and this free electron is responsible for conduction of electrical current. Now these are the 4 types of crystalline solids. Crystalline solids are 4 types. One is metallic solid, molecular solid, and network covalent solid, and ionic solid. Now in all these crystalline solid, perfect arrangement is there, and we view let us see the regular arrangement of particles in this crystal. So this regular arrangement of the particle in this crystal is called crystal lattice, or space is called crystal lattice, and each point in the crystal lattice is called crystal site or crystal point. So this is just like the points that you form, points that you add to do rangoli, and you do different forms out of these points. So it is a three-dimensional one, but Rangoli may be a two-dimensional one. Now you can see the arrangement of particles in the space, and there is a smallest portion, the smallest portion of the crystal lattice, which when repeated over and again, that generates the entire lattice. That is called a unit cell. A unit cell is the smallest portion of the crystal lattice, which repeated over and again will deduce the crystalline solid. Now this it is characterized by parameters, 6 parameters. 3 are the edges, length, breadth and height, and the angle between the planes alpha, beta and gamma. If these solids containing unit cells, and each unit cell has different geometry, and based on the arrangement of atoms in the unit cell, we can classify them as primitive or simple unit cell or centered unit cell. Primitive unit cell means constituent atoms are in the corners of a unit cell. The smallest portion, that is unit cell, in which atoms are present or constituent particles are present only at the corners, then it is a primitive unit cell. Suppose if it is centered unit cell. Centered means along with the particles which are there at the corners, some of the particles will be there present extra also. So this is body centered unit cell. It is a body centered unit cell when along with the particles at the corner, one more particle at the center is present. Now it is called face center if along with the particles at the corner, there are particles at the center of each face. There are 6 faces, and all 6 faces is having a particle at the center. So this is called face-centered unit cell. There may be end-centered unit cell. So alternate phases will be having, along with the corners, alternate phases will be having constituent particles. So primitive unit cell only at the corners, or it may be centered unit cell. And in centered unit cell, it may be body centered, simply called BCC, a face centered called FCC, or it is end centered EC. Now coming to the types of geometries that is possible for a unit cell. So on the basis of 6 parameters of the unit cell, the total number of possible unit cell in 3-dimensional lattice is 14. These are called Bravais lattices. So which are these? And each geometry is being named. There is cubic unit cell. If the geometry is called cubic, if all the 3 edges are equal, A is equal to B is equal to C, and alpha is equal to beta is equal to gamma is equal to 90. That means each angle also is 90, then it is a cubic unit cell. It can be tetragonal, rhombic, monoclinic, triclinic, trigonal or hexagonal. So there are 7 different kinds of geometries are possible, having variation in the edge length and the angle. So there are 7 crystal systems. It is called crystal systems. These are different because of the edge length and the bond angles. Now the Bravais lattices 14 are of this type. Primitive, end-centered, body-centered and face-centered. These 4 orthorhombic lattices are possible. Orthorhombic geometry can have these 4. And see this angle between them, and also simple the 3 cubic lattices, all these sides are same length and the angle. So there are 3 cubic unit cells are possible. And okay, And these three, that is, one is hexagonal can be one, and rhombohedral only can be primitive, and triclinic can be primitive. Out of all these arrangement, triclinic is considered to be the most unsymmetric. Here, A is not equal to B is not equal to C, and alpha is not equal to beta is not equal to gamma, which is not equal to 90 degree. So this is the arrangement of this type, and in this arrangement, there cannot be body centered, face centered, or end centered. All these three types, hexagonal, rhombohedral, and triclinic, exist only in primitive form. So, including all these types, there are 14 lattices possible, and these are called Bravais lattices. Now, how many atoms are there in a unit cell? In one unit cell, how many atoms could be there? Suppose you take a unit cell. Each unit cell here consisting of some fraction of atoms. This is the corner, and only 1/8 of that portion is inside the unit cell. So there are 8 corners, therefore the total number of effective atoms that could be there is 8 into 1/8, that can be 1 atom inside. So in a primitive unit cell, there can be only 1 atom possible. But in case of body centered unit cell, in case of BCC, see, there are, along with the corners, there is 1 whole atom inside. So 1/8 of 8 at the corner, and plus 1 whole it is there inside. Therefore, there are 2 atoms inside the body centered unit cell. Suppose if it is face centered unit cell, in the face centered unit cell, so along with the corners, that is 1/8 of 8 corners, there are atoms at the faces. How many faces are there? 6 faces are there. That means half of the 6 atoms also belongs to the unit cell. Half of 6 is 3. 3 plus 1, there are 4 atoms. So, in order to conclude, for simple primitive unit cell or simple cubic unit cell, there is only 1 atom inside the unit cell effectively. And if in case of BCC, there are 2 atoms, and for the FCC, there are 3 atoms. Now look into this particular video and try to understand more about it.
Is made of an infinite number of unit cells.
See the way the crystal lattice is present. So this is an atom, ion, or a molecule which is called lattice point. So this can be extended. That means it is the crystal lattice, and a portion of that is called unit cell. Unit cell may be simple primitive, body centered, or face centered. You can have a better view here. The atoms which I have shown here are made smaller because you can see the gap between them. What I mean is, in actual structure, these atoms which are binded are close. They are close enough, right? So there are 8 atoms at the corner. This is primitive, simple primitive unit cell, right? So these are called edges. So when these atoms are binded, there will be no gap like this. But in order to see the geometry, it is being shown like that. This is the actual structure of the atoms in the primitive unit cell. So these 2 atoms are binded, that means there is no gap between them. So edge length is equal to the R radius 1 and radius 2. So if these 2 are having same radius, that is 2R. So edge length, if you denote it by A is equal to 2R. This is how a 1 unit cell of the primitive unit cell is being seen. 1/8 of that portion is inside of it. 1/8 of the portion you can find inside the unit cell. So there is gap, there is void. It is called void, right? Gap. So this is the arrangement we show in order to get the concept of it. All these are equivalent way of seeing it. From different way it is to be seen. So in the primitive unit cell, 1/8 of age is there. That means one unit cell, one atom belongs to unit cell. Right? In case of body centered, there are 8 atoms at the corner. So this is the space filling model. Just look at that. These atoms are touching. Those which are at the diagonal are touching in face center. Those at the corners are not touching each other. This is a very important point. This is the space filling model. Is the exact way that atoms are present. Inside the unit cell, they look like this. Right? The point is very clear here. 1/8 of each atom at the corner belongs to unit cell, plus one atom totally which is inside, trapped inside. So there are 2 atoms inside the body center cubic unit cell. So again, 8 corner atoms, 1/8, and again 1 plus 1 at the center. Atom per unit cell. Due to atoms present at the corner is 1, and number of atoms at the center of the cube is 1. Therefore, totally there are 2 atoms. There are 2 atoms in this model, in this particular unit cell. Now in case of face-centered unit cell, there are 8 atoms at the corner, right? 8 atoms at the corner. Let you see the space filling model of it. Very important to understand. And there are 6 atoms at the corner, 8 atoms at the center, at the corner, and 6 atoms at the center of the face. Now this is how the edges of the unit cell looks like. So each atom belongs to different unit cells. Each atom belongs to 8 different unit cells. Therefore 1/8 of 8, this only belongs to 8. And this atom only half of that inside. Half belongs to another unit cell. Therefore, this is how it looks like. So number of atoms due to the one at the corner is 1/8 of 8. Same logic to be applied. Okay. Now 1/8 of 8. 1/8 of 8 corner atoms, that is totally 1. Now the atoms which are at the center. Atoms at the center. So there are 6 atoms at the center of the phases. So only half of that belongs to the unit cell. Therefore half of 6 is 3. So 3 atoms belongs to phase center unit cell. Right? So number of atoms per unit cell is an important concept in order to determine the density, in order to determine the density of a solid. We quickly look into the one which we have revised so far. Characteristics of solids. We have seen that classification of solids. Solids can be classified as crystalline or amorphous. So the crystalline solids may be molecular, ionic, metallic, and covalent solid based on the kind of interparticle force of attraction. And crystal lattice, what is meant by crystal lattice and lattice point we have seen. And the unit cell may be primitive or centered may be BCC, FCC or ECC. There are 14 types of brevis lattices, 7 primitive type and 7 centered. Number of atoms per unit cell for simple cubic, that is 1 atom, BCC 2 atom and FCC 4 atoms. Let us take up some of the questions which can be asked in this area. Write the feature that will distinguish between metallic solid and ionic solid. Ionic solid and metallic solid both are having some property alike like conductivity, but the reason for conductivity is different. Write the distinguishing feature of covalent solid. Why graphite is a good conductor of electricity although it is a network covalent solid. So these are the few questions. What type of interaction hold the molecular together in a polar molecule in a solid? So you look into the answer to these questions. Thank you.